with today's lecture, where we'll discuss axiom of probability and some simple counting rules. This is approximately chapter 1.2 in Kinsella and Berger for those of you who have the book and want to do some supplementary reading on this. So, first thing we're going to discuss is axiomatic probability. This is going to be a little bit theoretical, although nowhere near as bad as last Thursday's lecture, which might have had the ugliest theory in the entire course. So if I haven't scared you away yet, hopefully I'm not going to. But we're basically covering the question of what does probability mean in the first place. And the most commonly accepted definition, I know this is kind of fighting words if there's any Bayesians in the room, but the most commonly accepted definition is that if you have some sort of event that you suppose can be repeated indefinitely, and you have some idea of which outcome is more likely to happen, but it can't be predicted with perfect accuracy, then if we repeated this event an infinite number of times and then counted how many times this particular event occurred, then as the number of repetitions goes to infinity, then the probability would be the proportion of times that this particular event occurred. They said Bayesians would take an issue with this definition because you talk about something like, what's the probability of rain tomorrow? Well, the conditions tomorrow can never be exactly repeated, blah, 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 but we won't go into that. The intuition for the time being is just say, if in the ideal world, when we can repeat the weather conditions tomorrow an infinite number of times, then if it would rain 30% of the time when those conditions are repeated, then there would be a 30% probability of rain tomorrow. But in order to define this precisely in terms of math language, we need to be more precise about what we mean by event, independent, and convergence and so forth, which I'll do over the next set of slides. So these axioms of probability were defined by Kolmogorov in the early 20th century, and the three main axioms are the following: that say we have some event that's a subset of your sample space, and we want to assign a probability to this event. Well, Kolmogorov said that any probability measure has to satisfy the three conditions on this slide. That, first of all, the probability of the entire sample space is equal to 1. If your sample space is drawing one card from a deck of cards, the probability of drawing one of the 52 cards in the deck is equal to 1. The second condition is that it has to be non-negative, that the probability of any particular event may be 0, but it cannot be less than 0. And the final property is this countable additivity that, and it looks like there's a missing intersection sign on this slide. I'll try to remember to fix that. That if E1 to E2 up to En or even E infinity, there could be countably many of them, are mutually disjoint. That is, if EI intersect EJ is the empty set for all possible sets, then the probability of the union of these events is just the sum of the individual probabilities, which makes intuitive sense. The idea is that if two events cannot happen at the same time, then the probability of one or the other is just the sum of the individual probabilities. So since you cannot, if you draw one card from a deck of cards, you cannot draw the king of spades and the nine of clubs at the same time, so the probability of getting either the king of spades or the nine of clubs is just the probability of drawing one of them added together for both of them. And this last axiom is noted here has an implicit assumption that if you have an infinite sequence of events, then the union of all those things is an event. That if you're drawing from a sigma field, which under Kolmogorov's definition of probability, you have to be drawing from a sigma field or you get into the weird contradictions that I described last Thursday, then a countable union of things that are in a sigma field is still in the sigma field. So by definition, the union of all these events is still going to be in the sigma field. And so we say a probability measure is a measure defined on a sigma field of subsets of the sample space that satisfies Kolmogorov's axioms. And more formally, you should specify, when you define your probability space, you have to specify the full sample space, then a sigma field of subsets of your sample space where your probability is defined. As I said before, if your sample space is finite or countable, you'll usually just take all possible subsets of your sample space. If it's uncountably infinite, then you have to be more careful or you get weird contradictions. And then finally, you just have to define your probability measure. And for those of you who never intend to take 760, you probably can forget this definition once you're done with this homework, unless I decide to put it on the exam or something, which I probably won't. It's when you get into the measure theoretic probability in the more advanced classes that you need to worry about this. And we're just touching it briefly in this class so that to try to minimize the amount of pain when you do see this in the more advanced courses. Mm-hmm. Uh-huh. Yeah. If A is countable, in general, you can just let your sample space be all possible subsets of A without getting into any problems. But, again, that's probably beyond the scope of this class. And you can also show that for any probability function and any set in your on which your probability is defined, the probability of the empty set is always 0. The probability of any given event can be no greater than 1, and the probability of a complement of an event is just 1 minus the probability of the event itself, which hopefully agrees with your intuition. And you can also show that the probability of set A minus the probability of set B is equal to the probability of A minus the probability of A intersect B. Likewise, the probability of a union is probability A plus B minus probability A and B. And if A is a subset of B, then the probability of A is less than or equal to the probability of B. And if I'd been thinking, I would have added this picture to the slides, but if any of those properties aren't intuitive, doing something like Venn diagrams can make this easier to understand where these formulas come from. That say this is event A, this is event B. If you want to find the probability of A minus B, in other words, you chop off all of the part of A that's also contained in B. So it would be that section. You would take the probability of A, this whole thing, minus the probability that's in both, the intersected region. Similarly, if you wanted to find the probability that it's in A or B, you would take the probability that it's in A, this bubble, plus the probability that's in B, this bubble, and then you'd have to subtract off the intersection because you counted it twice. If you've ever been exposed to probability before, then these formulas are probably not new to you, but just thought I'd toss that out there. Also, if you have a probability function and C1 to C2 is some sort of partition of your sample space, then to find the probability of any given event, you can just take the intersection of A with each layer of the partition, and add all that together. That's a handy trick when you're doing proofs sometimes. And one property that I mention mainly because it's a special case of a more general case, the monotone convergence theorem once again, that we visited briefly in the first lecture, that a simple case that if you have a monotone sequence of events, that is, En is an increasing sequence of sets and they're all contained in your set of measurable sets, then the probability of the limit of these sets, that is, the probability of unioning all of them together, which of course is equivalent to just taking the limit of En, because is En because the union of all the ENs by definition is EN itself, since it's an increasing set, is just the limit of the individual probabilities. And likewise, if EN is a decreasing sequence of sets, then the probability of the limit is once again the limit of the probabilities. The implication here is that you can take the limit outside of the probability or inside of the probability if you want to. And in general, the monotone convergence theorem and the dominated convergence theorem, which I think are on the list of things they want the PhD students to know, give you the conditions under which you're allowed to take a limit inside a probability or inside an integral sign or a summation or whatever the case may be. Oh, those of you who are in the 690 PhD section, you'll probably get some problems and some reading on this later on. Master students, you can probably forget about it shortly. But just a simple proof of this to illustrate how you can do proofs in this types of things. I'll only prove the first half. Is I define a set of sets called F, where F1 is equal to E1, and for j greater than 1, Fj is defined to be Ej minus 1. So you can think of it if we have an increasing sequence of sets. Innermost circle is E1, then E2, then E3, then F1 would also be the innermost circle. F2 would be this part of E2 that's not contained in F1. F3 would be this outer ring, the part of E3 that's not contained in E1 or E2, and so on down the list. Why did I do that? Well, then the union of the ENs is going to be equal to the union of the FNs. And it looks like I forgot to note on this slide that the FNs are disjoint. If that's not obvious, I'll try to remember to make a note of that in case you're reading this later on. Well, basically, I've just created a bunch of disjoint sets that have the same union as the original E's. So to find the probability of the limits of the ENs, that's going to be equal to the probability of the union of the FNs. And since the FNs are disjoint, that's just going to be equal to the sum of the probabilities of the FNs by Kolmogorov's axioms. And that is, by the way, that I've defined the FNs is going to be equal to the probability of En minus probability of En minus 1 for each n. And if you expand that summation, all of the ENs will cancel except for the largest En. So for the sum for the first n terms will just be the probability of En. So as n goes to infinity, that's just going to be the limit of the probability that En goes to infinity. Yay, proof. Again, it's just to give an example of some of the tricks that you can use for these types of proofs, that sometimes when you need to do proofs involving like unions or sums or whatever, a handy way to do that is to just break it up into a set of disjoint sets where the nice rules apply. And another property of probabilities that also comes in handy when writing proofs sometimes is that for any given set of events, the probability of the union of the events will always be less than or equal to the probability of each event individually. And in fact, I mean, we know we have exact equality if the events are disjoint. If they're not disjoint, then this particular sum will always be no less than the probabilities of the individual event. I think I said that backwards, but hopefully you know what I mean. So that's the extent of our discussion on axiomatic probabilities. Now we're going to get into combinatorics and counting rules, which is basically if you're trying to calculate probabilities manually for some finite sample space, how would you go about doing that? Well, first of all, in formal probabilistic notation, that when you talk about a discrete sample space, what you're saying is the sample space is either finite or countably infinite. Countably infinite, hopefully you recognize the term by now if you haven't seen it previously. It just means that it can be placed into a one-to-one correspondence with the natural numbers, that you can just give subset 1 to the first element, subset 2 to the second element, subset 3 to the third, and so on, and list every single element in your set that way. So for example, famously, you can show that the rational numbers are countable, but the full set of real numbers are not. And when you have a discrete sample space, then in general, you can define your sigma field on which your probability is defined just to be the power set of your sample space, all possible subsets of it. In that case, the sum of all possible singleton events will always add up to 1. And in general, if you have a set that just contains all the points A1 up to AK, then the probability of A is just going to be the sum of the individual points. Sums of the probabilities of the individual points. So, a simple setting where you have a finite sample space with n elements and all the points are equally probable. This could be drawing from a deck of cards or rolling a single die or something like that. If we went with dice for a really simple example, you could say that your sample space is numbers 1, 2, 3, 4, 5, 6. There's a total of 6 of them, and all sample points are equally probable. In this case, the probability of drawing any one individual event is obviously 1 over 6, and the probability of getting, say, 1, 2, or 4 is obviously 1/2, just the sum of the individual probabilities. So all this counting and combinatorics, that was obviously a fairly straightforward example. All this counting and combinatorics examples that I'm going to give you here in a minute are concerned with if you're trying to find the probability of some event, just counting how many subsets of your sample space satisfy the property that you care about, and then just dividing by the total number of possible events. So if you have like a standard deck of cards and you draw a single card, they all have the same probability. So the probability of drawing a jack of hearts, one individual card, would be 1 over 52. The probability of drawing a club, there's 13 clubs in any deck of cards. The probability of drawing a club will be 13 out of 52, or 1 out of 4. If probability of drawing an ace, there's going to be 4 aces in a set of cards, 4 out of 52 once again. If you want to do something slightly more complicated and say the probability of an ace or a heart, then you have to use the summation probability rule that I described earlier. The probability of A union B is probability of A plus probability of B minus probability of A and B. So the probability of getting an ace is 4 out of 52. The probability of getting a heart is 13 out of 52. So that would be 17 out of 52. But you have to subtract the probability of both. That is, the probability that you get the ace of hearts. So you subtract 1 out of 52, you end up with 16 out of 52, as indicated on the slide here. And sometimes you will draw the event more than once. You could draw 2 cards. You could draw a card from the deck and then stick it back in the deck, reshuffle, and draw another one. Or you could roll your die twice. In that case, you would end up with 2 die rolls, the roll of the first die, the roll of the second die, and if you wanted, you could repeat this an arbitrary number of times, roll your die 12 times, whatever the case may be, and end up with multuplets in principle. So, for example, if, say, there's a college committee that's being created that there's a college committee with 3 freshmen, 4 sophomores, 5 juniors, 2 seniors, and you need to create a subcommittee of 1 person from each class. This is a simple example of the type of counting that we're doing here, just saying how many possible events are there in this outcome space. So if you want to say a probability of an event, then you just count how many, what proportion of the events of the total events satisfy whatever thing that you care about, and then you just divide to get your probability. So in this case, hopefully this is straightforward enough that the number of subcommittees would be 3 times 4 times 5 times 2, or 120 in this case. Similarly, if you live in a state with 7-digit license plates and the first 3 places are occupied by letters and the final 4 places are occupied by numbers, then the total number of possible license plates would be 26 times 26 times 26, 26 letters for 26 possible letters for the first 3 places, and then 10 possible numbers for the final 4 places. Oh, now we'll get into some counting and combinatorics rules. That a lot of probability questions just boil down to counting the total number of possible outcomes, counting the number of outcomes that you care about, and then dividing. And oftentimes these involve repeated selections from the same set of objects, drawing cards multiple times, rolling dice multiple times, and things like that. And if you want to count the number of possible outcomes, there's 2 things you have to consider. First of all, whether or not items are replaced after the selection. For example, if you're drawing a deck of cards and the first one is the King of Hearts, do you stick the King of Hearts back in the deck and reshuffle, or is the King of Hearts now removed from the deck and you can't draw it a second time? And whether or not the order of selection matters. That if I draw the King of Hearts and then say the 3 of Clubs and then the 7 of Diamonds, is and then I repeat the process and I get the 7 of diamonds followed by the 3 of clubs and then the king of hearts, the same 3 cards just in a different order, is that considered to be the same event or a different event? Depending on the problem at hand, you might care about either possibility, but the formula for counting the number of possibilities is different depending on whether or not the order of selection matters. So, I guess I basically just said this, that if you have a population of n elements and you select a certain subset in a certain orders, that's called an ordered sample of size R. And if you sample with replacement, that means each selection is made from the entire population. If you draw a card from a deck of cards, you stick the card back in the deck and reshuffle before drawing a second time, so you could end up drawing the same card twice. If you sample without replacement, then once it's chosen, it's removed from the population. You can't draw the same card twice. Obviously, in this case, the sample size can't exceed the number of possible elements in the population. And so in general, if you're doing sampling with replacement, if you have a population of n elements and a prescribed sample size R, then there's a total of n to the R different samples with replacement. Hopefully that's fairly intuitive. It's just there's n possibilities for the first draw, n possibilities for the second draw, n possibilities for the third draw, so the total number of possibilities just n times n times n r times. Easy enough. So, an example of this, say, like the Braille alphabet has 6 different locations that can be either raised or not raised. So how many combinations of raised / not raised locations are there? Hopefully that's obvious enough, 2 to the 6, because there's 2 possibilities at each position, a total of 6 positions, so 2 to the 6 different possibilities. In practice, there's only 2 to the 6 minus 1 total possibilities, because if there's no raised locations, then you couldn't tell that from blank paper, so they don't use that one. If you do sampling without replacement, then it's a little bit more complicated, but it's not that bad in principle. The basic idea is that, take the deck of cards example again. The first card you draw from the deck, there's 52 possibilities. The second time, you've removed 1 card from the deck, so there's only 51. The next time there's only 50. And so on down the line. So the formula ends up being n times n minus 1 times n minus 2 down to the number of things that you sample without replacement. And you can write that in math notation with this little factorial symbol. Hopefully you've seen this before. N factorial just means you multiply all the numbers 1 through n together. So 1 times 2 times 3 times 4 times 5 up to n. So in this case, a shorthand way of writing n times n minus 1 times n minus 2 is just to divide n factorial by n minus r factorial. If you write out the expression longhand, you'll see that everything except for the first r terms will cancel when you write it out like that. And an important special case occurs when r is exactly equal to n, that then the total number of possible samples is exactly equal to n factorial, and you say this is the number of permutations of a set of size n. You can think of it as, say, for example, a deck of cards. How many different ways can you given a deck of cards, how many different ways can you order this deck of cards, or things like that. I mean, it's hard to visualize with the deck of cards because the number is obviously huge. If I just had 3 sheets of paper, like 1, 2, or 3, then there's 6 possible orderings. It could be 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, etc. A total of 1 times 2 times 3, 3 factorial possible orderings. In general, this is said to be the number of possible permutations of a set of size n. So, a couple examples of this, and I guess we can do the audience participation thing to see if I've put everybody to sleep yet. Say you want to take a photo of 6 of your friends and you want to arrange them in a row. How many different possible ways can you do that?
6 factorial.
Straightforward enough. Is it 7:20? Okay, well, I put these together late at night. I'll try to fix that. Oh, slightly trickier one now. Let's say that you have 10 competitors. There's 4 from Russia, 3 from the US, 1 from Brazil, and 2 from Britain. And the tournament result just lists the nationalities of the players which place, and say it's listing all 10, then how many outcomes are possible? It's a little harder now because each element is not distinct. Does anyone have any idea of how you would tackle that one?
2 factorial over 4 factorial times 3 factorial.
Exactly. That the basic idea is there's 10 factorial possible orderings. So now let's take each one of these possible orderings. There's 4 Russians in the list, and so just let's say this is like during the Cold War where they're all genetically engineered to be super athletes, so the top 4 are all Russian. Well, we could have Russian 1, Russian 2, Russian 3, Russian 4 in that order, but it could be Russian 1, Russian 2, Russian 4, Russian 3, Russian 1, Russian 3, Russian 2, Russian 4, etc., etc. There's 4 factorial possible orderings of the 4 Russians. Similarly, there's 3 factorial possible orderings for the Americans, 2 possible orderings from the people from the UK. So in each case, if we just took all 10 factorial possible orderings, then the set of Russians would be repeated 24 times, the set of Americans would be repeated 6 times, etc. So we just divide by the number of possible orderings of the Russians times the number of possible orderings of the Americans, etc., etc. So you end up with a total of 10 factorial divided by 4 factorial times 3 factorial times 2 factorial. Make sense? Now the first problem with the twist. Say that you're inviting the same 6 friends to dinner. How many ways can you arrange them at your round dining table? Yep. Yeah. I mean, you can think of it, the easiest way to think of it to me is it's the same 6 factorial possible answers for the first question, except you can shift it anywhere from 0 units to 5 units to the right and have exactly the same ones. There's 6 different possible shifts, so we've increased the number of possibilities by a factor of 6. You just divide by 6 to get the number of possibilities, and you end up with 5 factorial. And this one, I guess, is kind of a rehash of the second one. Say you have 4 Martians, 3 Plutonians, 5 Jupiterians be seated in a row at an interplanetary conference. Hopefully at this point you can all scream at once that it's just going to be 12 factorial divided by 4 factorial times 3 factorial times 5 factorial. Similarly, if you want to find how many possible orderings of the word banana, Well, that's 6 factorial divided by 3 factorial times 2 factorial. Everybody with me so far?
So before that assumes the margins are all interchangeable.
Yeah. If they were not interchangeable, then it would just be 12 factorial total. So now let's give a couple more complicated examples. Let's say you have a population of size n, and you want to find the probability that a particular element will not be in a sample of size r. So say you sample without replacement, that the total number of and I should have paid closer attention to this because now I've confused myself. So you have a sample size and you want to find a probability that a particular element will not be in the sample size R. So the total, okay, yeah, the total number of samples that don't contain this particular element would just be n minus 1 factorial divided by n minus 1 minus r factorial, because obviously you just basically take that particular element, throw it out, and then count the total number of elements. Well, that's equivalent to just the number of samples without replacement from a sample of size n minus 1. And then you would divide that by the total number of samples, which both that include and do not include that particular element, which will be n factorial over n minus r factorial. So if you define Q to be the probability that an element's not in this particular sample, then the probability the element's not in the sample will just be the total number of events where it's not in the sample, i.e. n minus 1 factorial over n minus 1 minus r factorial, divided by the total number of samples down at the bottom, and you end up with that expression, which after some simplification looks like this, and then you end up with n minus r over n, which is equal to 1 minus r over n. So the probability that the element is in the sample is just r over n, which should agree with our intuition that if you're not replacing it, then the probability the particular element will not be in the sample is just the size of the sample divided by the total number of elements in the population. I mean, you probably could have done that figured that out intuitively without going through all these probabilistic counting applications. This is just to illustrate how this would be done. Let's say that you had to do it with replacement. This is slightly more complicated. In fact, as I recall, this exact problem, or something very close to it, ended up being on my qualifying exams when I took it back in the day. It's actually kind of a funny story about that they decided at the last minute that one of the problems on the exam was too hard, so they gave me this exact question instead. So, you never know when these things will pop up. And I got these notes from Mike Wu. He had no idea that this was an old qualifying exam problem for me. But in any case, in this case, if there is replacement, then the probability that any given element, the probability, I really need to sleep more before I lecture. The probability that for any given draw, the probability that it does not contain this particular element is obviously n minus 1 over r. So with replacement, you would just repeat that. You would just multiply that by itself r times. You end up with 1 minus 1 over n to the power of r. for the probability of not getting it, the probability of it actually being in your sample will end up being 1 minus that. And yeah, we had to do this a little bit more complicated because if you remember from calculus, as n becomes large, that converges to e to the something or another, which I'm not even going to try to remember the exact formula when I'm sleep deprived, but just thought I would point that out in case, like, I had to think of a qualifying exam question quickly, and hopefully you can remember this when I mention that in class. Anyway, so now let's say that you sample R items with replacement from a total of n. What's the probability of no repetitions in the sample? So the number of samples with no repetition is, we discussed earlier, will just be n factorial over n minus r factorial, and the total number of possible samples, of course, is just n to the r. So if you simplify this out, you end up with n times n minus 1 times n minus 2, etc., with a bunch of n's in the denominator, which can be written as 1 times 1 minus 1 over n times 1 minus 2 over n, etc., which is approximately equal to this. If that's not intuitively obvious, the idea here is that to get the 1, if you FOIL this all out, or the really long version of FOIL when you have multiplying more than one thing together, if you multiply all the 1's together, you get 1. Okay, that's easy enough. If you take 1 over n times 1 times 1 times 1, you get 1 over n. If you get 2 over n times 1 times 1 times 1, you get 2 over n. And the basic idea is that if you multiply 1 over n times 2 over n, you end up with an n squared in the denominator. If n's reasonably large, that's small. If you have an n cubed in the denominator, it gets even smaller. We're just going to ignore all those things with bigger powers of n in the denominator and assume they're close enough to 0 they don't really matter, and you end up with something that looks like this. And you can show, and you may have seen before from earlier math classes, that if the sum of the numbers 1 up to r minus 1 is just equal to r times r minus 1 divided by 2. So this is going to be approximately equal to 1 minus r times r minus 1 over 2 to the n. So the probability that there will be repetitions will be 1 minus that, which will be about r minus 1 times r over 2 to the n. No, it's 2n. If I said 2 to the n, like you said, I'm tired. Oh, to make this a bit more intuitive and also kind of a funner example, if you've heard of the birthday problem, what I just outlined on the previous slide is equivalent to the problem. Say you have a class of R people. What's the probability that some of these people have birthdays on the same day? If we disregard leap year babies, then there's 365 possible days that you can have birthdays. And we want to know what's the probability that at least one birthday is repeated. That's going to be equivalent to, we're basically sampling from the set of possible birthdays with a sample size equal to a class or whatever. And with the sample size equal to whatever, we want to know the probability that you get at least one event repeated. And that probability, based on the results of the previous slide, is going to be approximately equal to r times r minus 1 over 2 times n. N is 365 in this case, which actually increases a lot quicker than your intuition would expect it to. I I was going to calculate it for a size of our class, but I forgot. But my recollection is a class of about 30 or 40. It's not the point where it's an absolute certainty, but I think it's on the order of 70 to 80% that there'll be at least one repeated birthday in a class of about 40 people. So, okay, and obviously I should read my own slides, because it's already 80% with R equals 25, apparently.
But when R gets larger, it gets like accurate, because if R is equal to 30, then P is greater than 1, and you have to consider the terms where you have n0 and q or anything.
Right. And I mean, for practical purpose, if you wanted to calculate this probability exactly, you wouldn't use this formula. I mean, actually enumerating the total number of possibilities would be a major pain, but it's trivial to calculate using a computer, which people have done. And to have at least a 50-50 chance that two people in the class share the same birthday, you need a class of around 20, as it turns out. Oh. For additional reading, as I said, Chapter 1.2 in Casella and Berger, and wow, I'm done way under time. Again, despite the fact that I added more stuff. I think I talk too fast when I lecture. Any questions about any of this? Like I said, if you have issues with the homework, shoot me an email, come to office hours, whatever the case may be. I want to try to torture you as little as possible, and if you're interested at all in the discussion section, please fill out the poll.